Hi, welcome to another session of Basic Electrical Electronics Engineering. In today's class 7 under DC machines, we are going to list out the different types of DC machines. That is, we know that DC machines look like this. Now, based upon the input supply, the DC machine acts like generator or motor. And what we have got the information from our concluding classes that generated voltage or back EMF of DC machine is given by phi P and Z by 60 into A, where A is the number of parallel path, P is the number of poles, N is the speed, and Z is the number of conductors. And for lap kind of winding, the number of parallel paths is equal to the number of poles, and for wave winding, number of parallel paths is equal to 2, that is fixed. What is lap winding? What is wave winding? You can check out with our DC machine classes under class 2. Fine. Now our interest is to know the types of DC machines, right? So we have series generator and we have series motor, where the representation of series generator is in this way, where you can see the generated voltage, it is giving its energy to the load through the series field winding, and that is why it is known as series generator, where Vt is known as the terminal voltage, IL is known as the load current, ISE is known as the series current or series field current, IA is known as the armature current, and I is the actual current which is flowing into this closed circuit. Respectively, Ra is the armature resistance, RSE is the series field resistance, RL is the load resistance. EG is known as the generated voltage. When you compare the series generator with motor, it is quite opposite. What I mean to say is that the current which is flowing from generator to the load, whereas in the series motor, the supply is giving its input to the voltage which is developing in the armature. Now here the current flow is shown in anti-clockwise direction. IL you can treat here as the input line current. ISE is the series current, IA is the armature current, whereas EG and EB are representing the back EMF and generated voltage in motor and generator respectively. Now if at all you apply the uh, mesh analysis, and if at all you see the impact of series conditions here, whether it is generator or motor, the current is same. That is why in both the cases IA is equal to ISC is equal to IL, whereas in generator it is treated as load current, whereas in motor it is treated as line current. Now this is the important equation which is differentiating the generator from motor, that is the generated voltage is equal to the terminal voltage Vt plus, since we have the current in the series circuit as the same, so Ia of Ra plus Rse, whereas in the case of motor, here we have V in is equal to Eb plus Ia of Rse plus Ra. Now that is the basic difference between series motor and series generator. Now if at all you look into the shunt generator and shunt motor concept, the representation of the machine is almost the same. You can see EG, RSH and VT all are connected in parallel. Also in the case of motor, V in, EB, RSH are connected in parallel, where generator current IA is giving its current at this particular node, which is equivalent to IL plus IF. What is this IF? This IF is nothing but ISH. In different textbooks or in different literature, ISH and IF, they are termed in different fashion, but you should remember that the shunt field current is generally taken as IF or ISH. You please concentrate on this factor, where KCL is applied to this particular node and IA is equal to the two currents which is going away from this particular node. Now look back to the shunt motor. Here input is IL and the output is ISH and IA. So IL is equal to ISH plus IA. Now that is a basic difference between shunt generator, shunt motor in the form of currents. And when you frame the shunt current, it is nothing but terminal voltage which is across the load by RSH, that is the resistance of the parallel condition. And since it's a parallel representation of the shunt connection, the total voltage is terminal voltage, and that is why it is getting divided by the resistance in order to obtain the value of current according to Ohm's law. Fine. Now the same case for shunt motor, you can write ISH is equal to V in by RSH, where input is V in, that is supply voltage. Now when you compare the generated voltage equation, it is equal to Vt plus IaRa, and remember Ia is equal to IL plus IF, where in the case of motor, V in is equal to Eb plus IaRa. Now here Ia is equal to IL minus ISH. Now that's the important thing you should remember in your mind when you're dealing with the machines, especially shunt connection and series connection. The same logic will apply to short shunt compound generator or motor, where the diagrams you can see are quite most similar. Only a difference is that here in generator, the generated voltage is giving its armature current to the load and the shunt field connection, whereas in the motor, the supply voltage is delivering current IL to the parallel circuit which is connected in the form of RSH in parallel with RA. Now what happens in this case when you apply KCL? You will see that the series current is quite simple or equal to the load current, since it's a series connection, and also in the motor the line current is equivalent to the series current, whereas the armature current is equal to IL plus ISH in the case of generator, and IA is equal to IL minus ISH in the case of motor. Now with this, I can calculate the value of EG, which is equal to V plus IA RA plus IL RSC, and EB is equal to V minus IA RA minus IL RSE, right? And shunt field current is equal to V plus IL RSC by RSH, and ISH is equal to V minus IL RSC by RSH in the case of motor under shunt conditions of short compound conditions. I'm sorry for that. Right. What happens for the long shunt compound generator or motor case? You can see the representation of these two machines, where you can easily identify that ISC and IA in both the cases are equal. Only the difference is that in generator, IA is delivering the parallel supply, and in the case of motor, IL is delivering the parallel supply. Fine. What happens to the current conditions? You can see over here, IA is equal to IL plus ISH in the case of generator. In the case of motor, it is equal to IL minus ISH. Similarly, you can elaborate the conditions of current as Vt by RSH for generator, V in by RSH for motor, and then the total generated voltage is equal to the drop across the parallel elements, whereas EB is equal to the supply voltage minus the drop across the parallel elements. Fine. Now, if at all you want to compare the results of series motor and series generator in this fashion, you can directly take the formulas and you can remember the formulas in this fashion. Like in the case of series generator and series motor, the current conditions and voltage conditions. In the case of shunt generator and shunt motor, the current and voltage conditions. Similarly, in the case of compound machines, the short and long compound machines, you can have this voltage and current relations in this fashion. In fact, in a better way, I'll take generator and motor conditions for series connection, with the equations of current and voltage in this fashion. For shunt, the same thing, and for short shunt and for long shunt, I can have this entire picture as one concept in order to remember the things that is the difference between different types of DC machines in the name of generator and motor. So I hope you like this particular video. Please share among your friends and please subscribe to this channel for future notifications. Thank you.